Welcome to this video, What is a function? This video will give a basic concept of what a function is. In this video, Functions 101, there's a certain mindset that will help you learn the most from this video. First of all, this video is designed to give you a broad sense of what functions are and to familiarize you with function vocabulary and concepts. All the discussions and examples are idea-based, and this is not a how-to video. Please listen with the mindset that you're not being showed math procedures. You might have thoughts while listening like, where is he going with this? What steps do I follow? How do I start the problems? If you start to feel this way, remind yourself that this is not that kind of video. Just absorb the ideas. You may need to watch more than once. Let the journey of functions begin. I'd like to start by taking a guess at what you might think a function is. Have you ever been shown a function like this and asked a question like find f of 10? By the way, if you don't know how to do this, you're the perfect candidate for this video, because this is not something I've taught you yet. But maybe for those of you who do know this, you know to plug 10 into the function and work out the math, and the answer is 32. And while there's technically nothing wrong with any of this, this is completely valid mathematics, this is the perception that most people have of functions. And functions are so much more than this. The purpose of this video is to give you a much broader sense of what a function actually is, beyond what you may have been taught. Let's start with the definition of a function, some basic vocabulary and notation. Let's start with the actual definition of what a function is. A function is a collection of pairs, x, y, where no two different ordered pairs have the same x value. When you first hear this definition, it doesn't make any sense to most people. It's strange how mathematicians have defined a function. In this video, you'll see enough examples of functions where this definition will make sense. But let's focus on one phrase, collection of pairs. Here's an example of a function. You'll notice I have pairs of numbers, and that I've given this function a name. I've decided to call it m for no particular reason. All functions have a name, usually one letter long. But these four pairs, the collection of all of them as one entity, that is the function. The first item in the pair is often called the input, or just x. It used to be called the abscissa, but I haven't heard that terminology in decades. So we'll call the first number in the pair the input. The second one is called the output, or the y value. It used to be called the ordinate. So there's our output. And there's several different kinds of notation we can use to talk about these pairs. And you might wonder, well, if this function has four pairs in it, then there they are. What is there to talk about? Well, there's a lot of notation that has developed over the centuries that you have to familiarize yourself with. So watch this. All of these mean the same thing. Notice that the function m contains the pair 7, 2. Well, that's obvious. It's sitting right there in the function as one of the pairs. There's no mystery to that. Another way to say that is that an input of 7 leads to an output of 2. That means exactly the same thing, and sometimes we use sentences like that. We could also say when x is 7, y is 2. A more simple way of really just making the same statement. Another way to say it is m of 7 equals 2. Notice the m next to the parentheses with the 7 in it. Ordinarily in mathematics, two things next to each other when one of them is in parentheses means multiplication. This does not mean multiplication. M of 7 equals 2 is just another way of saying that the function contains the point 7, 2. We also say 7 maps to 2, or m maps 7 onto 2, and we use this little arrow as a mapping. The concept here behind functions is, yes, they are a collection of pairs, but we tend to think of them as, in some sense, an input and an output, or even a cause and an effect in some cases. And so this last line should be thought of as when 7 goes into the function, 2 as an output is the result. Let's now go through 6 basic ideas that I would like you to know about functions. Once again, here's our definition of a function. Idea number 1. Functions can be finite or infinite. Here's a function m that we just saw in the previous example. Here's a function q. Notice the phrase etc. at the bottom. M is a finite function. It only has 4 points. Finite meaning not infinite. By contrast, q is an infinite function. Notice, for example, wouldn't the function q contain the point 57, 570? That seems to be implied by the etc., meaning that the pattern continues. And this example should convince you that there are an infinite number of pairs in the function q. Idea number 2. Functions can be displayed graphically. I'll show you a couple of examples. First, here's a function that I've decided to call j for no particular reason. And notice that it has 5 points on this graph. Well, if a function is a collection of pairs, but each point on a graph is a x and y pair, then this is essentially just another way to represent a function. By the way, it's the same as if I listed out the ordered pairs that were on this graph. Just a couple of observations about j. First of all, notice that j of 2 equals 4. That's another restatement of the fact that j contains the point 2, 4. They're exactly the same statement. Notice that j of pi is 1. You may recall pi is approximately 3.14, and you may even be able to identify the point whose x-coordinate is pi. And it's also worth noting that function values can be undefined. Let me explain what I mean by that. j of 5 is undefined or does not exist because there is no point contained in this function whose input coordinate is 5. In other words, there's no point on this graph that has an x-coordinate of 5. Therefore, j of 5, which would ordinarily mean the y value when x is 5, doesn't exist because there is no point where x is 5. Here's another function displayed graphically. I've decided to call it z. The first thing worth noting is that z is an infinite number of points here. Now, you may not see any, quote, points on z at all, but consider the following. Z of 2 is 4. How do I know that? Z contains the point 2, 4. Now, something worth noting here is that these big visible round dots don't have to be there for the function to contain that point. This function is being expressed as a line, and that line passed through 2, 4. Whether you see a big obvious dot there or not, it still contains that point. Notice also that z of 5 is 10. Well, why is that? Well, because when x is 5, y is 10 in this function. But does this line contain that point? It absolutely does. Notice the arrow on the end of the line. If we were to extend this line, which is what the arrow implies, a forever extension, then we'll notice here, by extending the axis, that when we have an x-coordinate of 5, we have an output or y-coordinate of 10. You can tell that by the fact that the slope of this line is 2. It's clearly going up 2 spaces in the y direction every time x increases by 1. But you can infer from this that not only is z of 510, but for example z of 300 would be 600. You can't see that point in the picture, but this function contains the point 300, 600. In fact, it would be fair to say in general that this function contains z of any number whose value is found by just multiplying that number by 2. Idea number 3. Functions can be displayed algebraically. Let's take the function z that we just finished looking at and analyze it a little further. Z contains 2, 4, we saw that previously. It also contains 5, 10, but wouldn't it also contain 0, 0? And here's a seemingly random pair, 2.3, 4.6. I got that by picking a random number 2.3 and doubling it. It also contains negative 4, negative 8. You can't see that on the graph, but it would pass through that point. And it contains pi, 2 pi, for example, because the y value is twice the x, and so on. Notice that z contains an infinite number of points. There's no way to list them all, and so we use algebra symbols to represent the infinite number of points. In the previous slide, we discussed that you could describe this as z of any number is double that number, or that the y value is twice the x value. But we don't typically like to use any, the word any, in our formulas. So instead we would say z of x equals 2 times x. It's worth pointing out again that this x in parentheses is by no means a multiplication. This is read z of x, meaning the function z applied to the input of x gives the value of twice that value of x as its y or output value. The multiplication sign we don't typically use in algebra, so I'll take that out, and this function would be valid where x is any real number. Just to say a little bit more about this, when we're using algebra notation, we typically use x as our input variable. We don't have to, we could have put any letter there, but the tradition is to have x be your input value, and whatever the formula is doing to that, in this case doubling it, as our output value. By the way, this could also be written in the following notation, which could be read, the function z maps x onto 2x. It looks different, but it would mean exactly the same thing. Idea number 4. Functions can be created without algebra at all. Here's an example of a function that wouldn't involve algebra. Before we show you the function, this is a calendar that represents meetings that a person attended in the month of July. You can see the meeting times in red, shown here. We're going to let the function m be the total number of meetings that this person attended from the first through the end of day D of July. Now, that doesn't sound like the way most people speak. This is sort of a mathematical way of defining a function. And to help you understand the function better, let me try to breathe some life into this using plain English. Before I do, though, I want to focus on the word let. Let is one of the most important words in mathematics. It is a clue to you, the reader, that the person writing the sentence is defining something that before this moment didn't exist. It's basically a definition word. So whenever you see the word let, your brain should send you a message. This person is about to give me a definition of something, and then read it in that context. Okay, so now what does this function actually mean? Well, to understand that, let's ask the question, how many meetings had they attended between the first and the end of the day of the 5th? Well, looking at their calendar, they attended 4 meetings between the 1st and the end of the day on the 5th. So we would mathematically say that m of 5 equals 4. That's just another way of saying this function contains the pair 5, 4. That's just another way of saying that by the end of the 5th, they had attended 4 meetings. Now let's read the definition again right under the calendar. We're going to let the function m of d be the total number of meetings that this person attended between the 1st and the end of the day d of July. And so I hope that definition makes a little bit more sense in reading it. If not, I'll give some more examples. It turns out for this person's calendar that m of 1 is 0. What does that mean? That means by the first day of the month, they had attended 0 meetings. M of 8 is 7. What does that mean in this context? By the end of July 8th, this person had attended 7 meetings. Go ahead and look at the calendar and see if you can find the 7 meetings that they had attended by the 8th. By the way, it's worth noting that m of 9 is also 7, because by the end of the day on the 9th, they had still only attended 7 meetings. Notice also that m of 31 equals 20. That represents that by the 31st of July, they had attended 20 meetings. And if you look at the calendar, you'll see there are in fact 20 meetings. It's also worth noting that m of 37 is undefined. Why? Because there's no such thing as the 37th of July. Likewise, m of 13.2 is undefined. Same reasoning. The 13.2 day of July doesn't really make much sense. So that's also undefined. Idea number 5. Functions don't need to involve numbers at all. Here's an example. I'll pause while you read this. This is mathematical speak for a pretty simple idea. I'll give you an example. My mom's name is Barbara. So this function, we could say, includes Franz Resiedlo, Barbara Resiedlo. In other words, me, comma, my mother. But it also includes my sister, comma, Barbara Resiedlo, since, of course, she's also the mother of my sister. And it also includes Barbara Resiedlo, comma, my grandmother Eleanor, which is her mother. Pretty basic concept. This function illustrates that functions are pairs of things and don't actually have to have numbers whatsoever. It's worth noting that P1 is a finite function because it only has billions of ordered pairs, not an infinite number. Idea number 6. Not all collections of ordered pairs are functions. But wait, didn't I say earlier that a function is a collection of ordered pairs? Yes, that's true. A function is a collection of ordered pairs, but there are also collections of ordered pairs that are not functions. And that's what we're going to see here with 2 different examples. Here's the first one. Consider the set of all ordered pairs password username for a particular public website. Let's call this collection K for no particular reason. And suppose in this public website with potentially millions of users, suppose there are 2 of them that both chose I love money 1000 as their password for the website. Well, since our collection of ordered pairs is password comma username, then this collection K would contain both I love money 1000 Jonathan 2003 for that user, but it would also contain I love money 1000 Sarah Peterson. And why would this cause the collection K not to be a function? Well, look at the definition of a function. Not all collections of ordered pairs are functions, only those for which no 2 different ordered pairs have the same x value. But look at the bottom of your screen here. Here are specifically two ordered pairs that do have the same x value. And therefore, this collection of ordered pairs is not a function. Now, this problem looked at password first and username second. What if we were to consider a different collection? I won't name it, but something other than k, or the same data as k, where the username and the password were switched. Suppose the username were the x-coordinate. This turns out that it would be a function if we considered this collection. We could call this function validateUser. Now, most functions in math are a single letter. So far we've used m, q, j, z, m, and p1. But the name of a function doesn't have to be a single letter. It could be 11 letters long like this one. In fact, in computer programming, the functions tend to have very long and descriptive names to help the programmers understand the functions they're using. But let's look at this in a more mathematical sense. I have a question for you to ponder. Don't you hate it when a website says that a particular username is unavailable? I don't have that problem often with the last name of Rosillo, but more common usernames are often taken before you can get to them. Now, this seems like a strange question to ask you during a math video, but it's pertinent to this particular function, validateUser. A website won't allow two usernames to be the same. It wouldn't function under those circumstances. So if we consider all the ordered pairs username comma password, if username is in the x-coordinate, then the fact that no two usernames are the same, in other words, the fact that there are no pairs with the same x-coordinate, would make validateUser a legitimate function. And just to go a little bit further, computer programmers use code all the time. I won't show you any specific code here, but there are lots of if-then statements in computer programming. For example, if in this particular context, if validateUser applied to your username equals your password, then of course you'll be granted access to the website. This example shows that functions transcend mathematics and play a very important role in the world of computer science. Let's look at our second example of idea number 6, that not all collections of ordered pairs are functions. Consider the following set. Imagine all the pairs of numbers x, y, for which the x-coordinate equals y squared, or the y-coordinate squared. Let's call this collection of pairs T, for no particular reason. Just to get a sense of what T looks like, let's pick some random examples from this collection of pairs. If my y-coordinate were 3, looking at the equation near the top right of your screen, if y were 3, x would have to be 3 squared, or 9. Convince yourself that this ordered pair is a member of the collection T. It essentially is, because 3 squared equals 9, or more generally, y squared equals x. If we wanted there to be a point whose y-coordinate was -5, the x-coordinate would have to be +25, because -5 squared is 25. You get the pattern, hopefully. T also contains 0, 0, because 0 squared is 0. It also contains radical 7, 7, because if you square radical 7, you get 7. If you're watching this video with no knowledge of radicals, don't worry, that's not where we're going with this example. And T also contains -3 as a y-coordinate and 9 as an x-coordinate, because -3 squared is 9. Now, T contains an infinite number of pairs. This is just a quick showing of 5 of them. But there's something worth noting here. There's something about these two in particular that you see highlighted that shows us that T, the collection T, is not a function. Look at the definition at the top. This is a direct violation of the definition. No two different ordered pairs may have the same x value, but these two different ordered pairs have the same x value, and for that reason, t is not a function. Let's just go down another road here where we examine what would happen if we were allowed t to be a function. We're not going to, it isn't a function, but I want to give you a sense of why they chose the definition for function that they did. If we were to allow a situation like this to be a function, 9 would map to 3, but 9 would also map to -3, you'll notice by looking at the two highlighted ordered pairs. But the very concept of a function is that inputs map to a specific output, not that an input can map to two different outputs. That concept that each input should map to a single output is violated here, and that is why they wrote the definition the way they did, to make things like this not be a function. By contrast, it is okay to have two different inputs that map to the same output. For example, take the mother function that we examined earlier. In that function, we saw that it contained these two ordered pairs. Restated, both me and my sister map onto our mother, and that's the way this mother function was written. For that reason, you can see that two different inputs map onto the same output. This is fine. Despite this duplication, P1 is still a function. In other words, it's okay for two different inputs to map to the same output. It is not okay for two different outputs to map to the same input. Of course, this raises an interesting question. What do we call a collection of ordered pairs if it fails to meet the definition of a function? In other words, what do we call t here? We can't call it a function. Well, there's no actual name for it, but here's a word worth knowing. Collections of pairs, whether they're functions or not, are called relations. If you just wrote down a random bunch of pairs of things, that is by definition a relation. Now, before we proceed, I'm going to pause. Please read idea number 6 near the top of your screen to yourself. In light of that, here's a restatement of idea number 6. Some relations are functions, while other relations are not. In other words, a relation is a collection of ordered pairs. Sometimes that turns out to be a function, and sometimes when there are duplicate x values, it's not a function. But that still leaves the question, what do we call this x equals y squared collection of points? Well, what's the word for a collection of pairs which is not a function? Unfortunately, nobody ever made up a word for that, so we just call it a relation which is not a function. And that completes the first of our 2 videos in this series.